So I can start. Okay, so welcome to another GADEP seminar. So Babak is going to talk about flat connections from irregular conformal blocks. Okay, Babak.
Okay, yeah. Hello everyone. Thanks very much to Hossein for the invitation. And yeah, it's the first time that I'm speaking in the seminar series, and very excited to do it. So although it's a bit late here, but yeah, let's see how I do. So yeah, this is about flat connections from irregular conformal blocks, and the title is the same as the title of a paper which appeared on the archive a couple of months ago, and it's joint work with Ihua Liu and Nikolai Reshetikin. And well, it is about conformal blocks, as the title says, and conformal blocks are ingredients of partition functions of two-dimensional conformal quantum field theories. And an important property of these, I mean, of course, this is a mathematical physics paper, so there is a lot of physics in it, but in this talk, I will focus on the mathematics and try to maybe I will use some physics phrases, but I will try to put it all in the context of mathematics. So just bear with me. So conformal blocks are basically, from the mathematics point of view, I mean, they are physical building blocks, but they are known to be sections of vector bundles. Okay. And this is definitely the case for so-called rational CFTs. So we have rational CFTs, and anything beyond that has to do, this terminology has to do with the central charge, something called the central charge, whether it's a rational number or not. And so these are sections of finite dimensional vector bundles. And moreover, what has been less studied is so-called irrational CFTs. And one example here is the 2D Liouville CFTs. And this one can actually have so-called irregular operators. So these rational CFTs, they usually only have regular operators, and these conformal blocks are correlation functions of regular operators. So we are dealing with certain correlation functions of certain operators inserted. But let's say we are on the sphere, on the two-sphere. So it's a two-dimensional theory. You have to pick a Riemann surface. Let's pick the two-sphere. And we put certain operators on points of this two-sphere. And this delta 1, delta 2, and so on are so-called conformal weights. Basically, their highest weight with respect to the Virasoro algebra. So these are highest weight states, if you want, of the Virasoro algebra. But then we can have certain operators which I denote by I. These are irregular operators. They are not highest weight operators. They are in different representations. So these guys are highest weight, or in other words, conformal primaries. And this one is an basically irregular vertex operator. And again, as I said, we are kind of on the sphere, and we have certain points here on the sphere, and I'm inserting, let's say, at this point, O delta 1 at the point Z1, and O delta 2 at the point Z2, and so on and so forth. Okay, on the two sphere. So now, what are these irregular operators? So Well, I'm going to answer this in a moment from representation theory point of view, but before coming to that, what is more relevant for me or for this paper is basically the characterizations of sections of line bundles. And here we can actually answer this question very easily. So now consider such a conformal block. So we take basically an operator at Z0, another operator at Z1, and so on. Basically not Z1, Z, and then Z1, and so on and so forth. So these are conformal blocks. So this will be, as I said before, these conformal blocks are sections of vector bundles. So this is a vector in some sense. Then this phi can have singularities. So near these points zi, so when z approaches zi, and we subdivide between two types of singularities, so we can have this conformal block as a function of z, and if you take its derivative, then it is basically near z0. Say we are approaching the point, we let the point z approach the point z0, then the behavior is like this. It kind of blows up, and this a0 is some matrix acting on this vector, and there is a here you say that we have a regular singularity. And what we can also have is that we have these conformal blocks, and near z0 they show a behavior of the following form. And in this case, so r is here greater than 1. When r is greater than 1, we call it irregular. Okay. Now, of course, from the point of view, well, this is a first order vector valued ODE, but you can also view it as a higher order ODE if you focus on one of the components, so the corresponding higher order ODE is then the following one. So you have D and F dzn plus P1z d to the n minus 1 f n minus 1, and so on, P and z, and the other one is just f itself is equal to 0. And this is irregular if and only if basically z minus z0 to the power n Pn is not analytic around z0. So in that case, it's called irregular, and then there's a whole mathematics theory, of course, where the solutions can be only obtained as asymptotic series, and they are not convergent, and so on and so forth. So this is the behavior of these conformal blocks or physical correlation functions for these irregular operators. So if there is an irregular operator at this z0, now I want to so this was basically the motivation to study such operators. Now I want to come to the real thing, namely, I want to look at irregular representations of the Virasoro algebra. So okay, let's look into that then. So we have the following definition. So we have the Virasoro generators, Ln, L minus n, and so on. And if I take L to R acting on this irregular state, then it is supposed to be an eigenstate. And Lm acting on this I is equal to 0 whenever m is greater than 2r. And moreover, we have L 2r minus 1 acting on it. This one will be also an eigenstate with eigenvalue lambda r minus 1, and so on and so forth. So there is a kind of pattern here, and until you reach, of course, L0, and this R here is known as the rank. So what is different from here, with, if you compare to highest weight representations, is that all the positive modes of the Virasoro generator, so Ln for n greater 0, they should usually annihilate the state. So this is the usual highest weight story. But in this case, you see that we take finite number of these guys, and they do not annihilate it, but they act kind of non-trivially on it. Yeah, let me specify the action actually in the simplest case, which will be relevant for us. So in the rank 1 case, we have then the following. So L2 acting on the state I alpha C. So the state is parameterized by complex numbers alpha and C, and you get minus C squared over 4 times I alpha C. So it's an eigenstate of L2. L1, under the action of L1, it's again an eigenstate with this kind of eigenvalue. So this Q here, this Q is B plus B inverse. B is a complex number. This B is a parameter of Liouville theory, of this Liouville CFT. It parameterizes the theory. So there is a one parameter deformation of the theory, which is basically given by this B. So don't worry about that. And L0 now this is the one which usually, in the usual representations, L1 and L2 would annihilate the state, and the negative modes create descendants, and L0, under the action of L0, it's an eigenstate. But here, under the action of L0, it's actually not an eigenstate. It basically doesn't act, it acts non-diagonally. You have to take this logarithmic derivative with respect to C. So that's how the action of L0 is in this case. And alpha here is something which is called a Liouville momentum. And you see if the C is 0, so if you are dealing with an actual regular representation and C is 0, then alpha here, then the action under L1 and L2 becomes 0, and under L0 you just get delta alpha, so you recover the usual highest weight representations where delta alpha is the highest is the weight, right? And it's a function of this alpha, and yeah, I think this delta alpha is roughly alpha times q minus alpha. So let's also write this down, and delta alpha is equal to alpha q minus alpha. This is in the usual circumstances, this would be the highest weight. Now, what one can do is one can actually construct these states by using the so-called state operator correspondence. So one can show that actually this irregular state I alpha C is obtained by an irregular operator acting on the vacuum, if you want, the 0. And this irregular operator, this is the normal ordering of the exponential of 2 alpha chi L times exponential of C del chi L, where with L going to infinity. So L is the insertion point of the operator, and we put the irregular operator at infinity. And chi is just a chiral bosonic field, so it appears in a Lagrangian, and this is the corresponding vertex operator. That's how we call it in physics. Now, this is my brief kind of discussion of these representations, but I want to come to differential equations, as I promised you earlier. So how do we obtain differential equations from all this representation theory, right? So that's the main thing I want to come to. But maybe, yeah, any questions so far about this, the business of these representations? Maybe it was brief, but maybe there are still some questions. Or okay,
Yeah,
then let me Yeah.
I'm trying to explain my students something. Okay.
Right. So then let me come to the differential equation point of view. So we, in this irregular case, we obtain so-called modified BPZ equations. So this BPZ is coming from the three Russian guys, Belavin, Polyakov, Zamolodchikov, and who first discovered these equations. So yeah, consider now the so-called degenerate primary state. So this is now a primary state. It's not an irregular one. It's a regular one, where V minus 1 over 2B alpha. So acting on 0 on the vacuum. So let's also denote the corresponding state in this way. And this V alpha here is just a normal ordering of e to the 2 alpha chi, right? So it's basically, that's what this vertex, the regular vertex operator is. So you see here, if you compare this to this guy, you see that the irregular one has this derivative piece. If you set c to 0, you recover the usual regular stuff. So this one is the irregular piece, and this one is the regular piece. And here you see that this guy just consists of this regular part. And you act with this on the vacuum and you generate the state. And it has some conformal weight, which is minus 1 over 2b times q plus 1 over 2b, right? Now, why is it called the degenerate? So we said it's a degenerate primary. The reason is that if you apply with Virasoro descendants, so the negative modes of the Virasoro algebra, then you eventually will generate a null state. So you will reach a state which is again just 0, or it has 0 norm with other states, 0 scalar product. So you have to mod out the module generated by that. And this is this L minus 2 plus B squared L minus 1 squared acting on V, acting in this way. So this is now a so-called null state. So it is basically 0. So then, but that implies that if you now consider a correlation function with such a degenerate operator, so for example, let's consider this particular correlation function, I'm now going to include an irregular operator at infinity, but then a bunch of regular ones, which are degenerate at z, at z0, and at z1. Okay. So then, of course, if you now act with this operator L minus 2 plus b square L minus 1 square on this function, once it hits the degenerate operator, it is 0, right? So therefore, we obtain the following differential equation. So we have this L minus 2. So the L minus 2 acts on these states. This is just an operator, but on the conformal blocks, it actually acts as, so on this F, which is a function or a section of bundle, it acts as a, so the second derivative with respect to z. So L minus 1 just acts as a derivative with respect to z, and L minus 2, the action of L minus 2 is specified in this way. So you obtain, so this is the action of L minus 1 squared, but then L minus 2 acts as z1 minus z squared plus delta z0 minus z1 squared minus 1 over z1 minus z del z1 minus 1 over z0 minus z1 del z0 minus c squared over 4 f and this is my equation, and this is a null state in a sense that this whole thing should be 0. Okay, so because of the null state, so this operator acts, and you commute it past all the operators inside these inside this correlation function here, and then it picks up all these terms. And
so it has only derivation with respect to z and z1, no? Or just a minute.
Well, derivation only with respect to z. Z1, there is no derivation. You just have these terms.
The second
Z1
derivation is you wrote it z1, or it's a mistake.
No, this is z. There is only one derivation. Oh, there is. Oh,
the
good,
second
good.
the z1.
Yeah,
so
this one.
this
one. That's correct. That's correct. Yeah. So indeed, there is one z and one z1 and one z0 actually. Right. So you have the derivation with respect to all of them, but you want actually a differential operator with respect to one variable only. So you have to get rid of z1 and z0 somehow. And the way to do this is as follows. So you're going to use global conformal invariance.
So delta was a constant or the function of z?
Delta is a constant.
Okay.
Is this constant -1 here? -1 over 2b, q plus 1 over 2b. Q is z independent, and everything is z independent. It's the highest weight, is the weight of the representation. So it's z independent. Now you have to use two more equations, namely L0 and L -1 invariance of the vacuum. So what do they do? So L -1 invariance. How does L -1 act? It acts on all the fields. So it acts, for example, the L -1 here. It will act on z1 first, right? That's where this term comes from, and then it acts on z0 and on z, and finally it acts on this irregular piece, right? So let's write it down. So the action of on z1 is just the derivative, on z0 the same, because these are all regular fields. On regular fields, it just acts as a differential operator with respect to the argument. But then on this irregular one, we look at this representation here, and it acts in this way. So we have to add, instead of a derivative, we add just this constant, c times alpha minus q. So you add c times alpha minus q here, times f is 0. So the way it works is that you insert this L -1. You see, the way this equation is obtained, you insert the L -1 here. Well, it acts on the, here you insert some L -1, then it acts on the vacuum, right? And it just annihilates it, because the vacuum is invariant under it. But then by using commutation, hmm? This is one of them is DDZ. Yeah, right, like this. Or let's say the first one is DZ, DZ0, DZ1, like this. Okay. It acts on all of them. So the way it works, the vacuum is invariant, so it's 0. But then you can commute it past all the other operators. And okay, maybe okay. Let me tell you how to do this. Let me tell you how to actually do this. Good. Let me draw a little picture so that it becomes crystal clear. Is that you know the physics here? Let me first write down also the corresponding equation for L0, because the L0 invariance is coming as follows: z del z plus z0 del z0 plus z1 del z1 plus 3 delta minus c del c plus delta alpha f is 0. So now how did I obtain these two equations? So suppose again I'm on my sphere, right? Okay. Yeah, I'm on my sphere and I have these operators, right? And so on and so forth. So something like this. So suppose this one is the irregular one. This is one regular operator, another regular operator, and somewhere there is just the point 0. So there is the vacuum. There is nothing there, right? I'm going to take an L0 operator, and the L0 operator, when it acts so these operators, when they act, you can think of them as kind of these circles. Oh, sorry. As the circle encircling this 0 point, and it's 0 because it acts on 0, right? So, but then L0 or L minus 1, both. But then you can view this circle as a kind of by the same token, because you're on the sphere, you can actually think of the circle as encircling the other guys, right? It's the same thing, because well, the way it works is that maybe it goes in this way, but then you can think of it as basically you pull this string around, and now the circle goes around the other operators. You see what I mean? So this is how you do the computation. So since this result is 0, right, this gives 0, and the other result just gives you all the action of these operators on the other states, and these are the four terms you see in each of these equations. So that's how this is derived, okay? And now you see that we have this L0 and minus 1 invariance. We have these two equations. We have two equations, but we can now solve using these two equations. We can solve for dd0 and ddz1. We solve just for these two in terms of ddz, okay? And then we can insert it back into our equation star here, right? So so combining with star finally gives that now I'm setting for simplicity z1 is equal to 1 and z0 is equal to 0. I can use conformal transformations to do that. Then I have this story. Right. Now I obtain finally a differential operator solely with respect to z. Okay. So this is my equation, my previous equation for coming from the null state. And now I have only a differential equation with respect to z. The dz0 and z1 disappeared because I used the other two equations to solve for them. And yes, now, okay, this is, of course, c is still a parameter, and I still have, in a truest sense, this is not an ordinary differential equation. It's something like a partial differential equation, because I have also derivative with respect to c. And I want to get rid of it, actually, because I want to obtain an ODE, a pure ODE with respect to z. But here it appears, but that's just a remnant of the fact that these representations are defined in this way, because you see this L0 just acts in this particular with this logarithmic derivative with respect to c, and c was just a parameter, and this is a remnant of that. But yeah, at the end, I will actually get rid of it. I will find another equation where I don't have this DDC. And but apart from that, it is just a second order differential equation. So now I have this differential equation, And next thing is I want to find solutions for this. And in physics, the solutions we are interested in are integral representations. So we want to come to integral representations. So I want to write this f as an integral of a kernel. So in order to do that, one has to introduce so-called screening charges. So this is some physics terminology at positions wi, and then the corresponding conformal blocks or solutions are given by integrals. So this is now the conjecture which we're going to prove, and this Ka, R, and Z of the following form. So F is now dependent on a cycle gamma. So I'm integrating over a cycle, and the integrand is this function nu of all the fields inside. The screening charges have Liouville momentum 1 over b, and the irregular operators have Liouville momentum minus Ka over 2b, Za, and then I have an irregular operator at infinity. And I have, of course, the measure dw. I have to integrate over the position of screening charges. These are auxiliary charges which I include on the sphere to have charge conservation, because there is a U1 symmetry, and these alphas, these sub-indices here, these are like charges. And by Gauss' law, I need to have charge conservation. All the charges have to cancel. So in order to compute these things, you insert finite number of screening charges W, and you integrate over their position, because they can be anywhere, to smear them out. And that's how this is computed. And let me now define this piece here. This is called a Wick contraction in physics. And I'm going to write this actually as an exponential of some superpotential W over B square. And we'll see in a moment what that is. And this nu here is the so-called Wick contraction. And this gamma here is a so-called Lefschetz thimble. That's what it is called. And the way it is defined is that if you have, let's say, one screening charge W, then let's say this is this W plane, right? Then the cycle gamma is kind of defined as what? It's basically this red line here. And the crucial property of this is that at its two ends, this W over B squared goes to minus infinity. So if W over B squared goes to minus infinity, of course, this exponential here is suppressed and everything is well defined. The integral is convergent. And this W, so we just...
That's just a question. To have Lifshitz dimple, you must have vibration. But what is the vibration? No?
There's what I mean by vibration. I mean, okay. It is a cycle, a cycle in relative homology, right?
Okay.
In this W plane, and it is relative in a sense that the endpoints are in where this superpotential W over B squared goes to minus infinity, relative with respect to that condition.
What's the dimension of gamma? Dimension of this integral?
This is a middle dimensional thing. So if your W plane, if you have just one screening charge, you have the W plane is the C plane, and this gamma is just a one-dimensional cycle there, real one-dimensional, but otherwise it's a middle dimensional thing, right? So for arbitrary number of screening charges, okay? So this is these Lefschetz thimbles. So let's put it here. And now we also want to compute this integrand, this by the physics procedure which is called Wick contraction. So This is all physical intuition that the integrand should be like this, and then I'm going to prove it actually, that it satisfies the correct differential equations. Okay, so I'm going to compute the Wick contraction of these operators, and this is basically so in this Wick contraction you have to take the Green's function of all pairings. So this is how you compute Feynman diagrams. If you have some operators, you have to compute the Green function product. It's the partition function is, or the path integral is the product of Green's function, which are obtained by all pairings of two operators. So you have to take all possible pairings. This is Wick's theorem. And you have these, of course, screening charges with each other. So they produce this factor when you contract them. You have a screening charge with a regular operator, ZA. This produces this factor when you contract them. And you have the regular operators between each other. So ZA minus ZB. And it is minus KA minus KB over 2B squared. But then we have the irregular business. So we have to contract all the other fields with the irregular one. So if we contract, so there it always produces a lambda over B squared term, sum over IWI by contracting all the screening charges with it, and all the regular operators. They have a conformal weight, which is, or Liouville momentum, which is rescaled by 1/2. So it is, yeah, that's what you obtain. Okay, it's like this, where basically C is lambda over B. So if you plug in for C lambda over B, then you will, it's more convenient to work with this lambda instead of C. So lambda is just C rescaled by B, and that's what you get. Okay. Now this is the integrand. This is the, and then in the following, so we're gonna focus on the case where there is only one screening charge, right? So this gamma, as Hossein was asking, is just a one cycle in W plane. So this is just a real one-dimensional cycle, okay? So far, so good. So now I come to my main part, namely part 3, which deals with so-called flat connections. Okay. Okay. So now we're going to define the following function. Phi gamma is a function of z. This is integral over this Lefschetz thimble dw, because I have only one w now. Product I, w minus zi to the ki over b squared e to the lambda over b squared w. Okay? This whole thing I'm going to call the exponential of I to simplify my notation, and I is the logarithm of this business then. And then if you define this function phi gamma, then this original correlation, physical correlation function f gamma is just, if you look upstairs, because f gamma was the integral over this nu, and this nu is this kernel there, you get product over I e to the minus lambda over 2b squared zi times product over I not equal to j zi minus zj minus ki kj over 2b squared times pi gamma of z. So this phi gamma contains all the non-trivial business of the integral. Because the other piece, which is only z dependent, z is just a constant. You don't integrate over this. This you can pull out of the integral, right? So you have this original integral. If you plug in this function mu, you see that there are certain parts like this and like this. They are completely w independent. So you can take them out of the integral. And then everything which is non-trivial is then in this function phi. So that's how this function, so that henceforth we will be interested in this function phi. So this is my double star equation here. And then we have the following theorem. So first, define now the following vector, psi, which is defined as the derivatives of this phi with respect to z1, z2, and so on, all the way until you reach zn, where n is the number of your operators, the total number you have. Then we have two results. Psi now satisfies the differential equation del zi psi is ai psi plus sum over j not equal to I omega ij over zi minus zj psi, where this a here and omega, these are matrices, and they have the following structure. So a looks like this. You have 0, 0, 0. Well, then you have eventually lambda over p squared, but then you have 0, 0, 0. And so this is very simple, this matrix A. And then we have the matrix omega ij, slightly more non-trivial. And here you have 0, 0, 0, 0. Sorry, 0. Then you have 0, 0, 0. And you have ki over k. I actually can just write ki, and I'm going to write okay. I'm going to write it as follows. Omega ij is equal 1 over p squared, ki minus kj minus ki kj. And you basically have everywhere else just some zeros, okay? And so on. And this is the entry ji, and here you have again j and I. The j's and i's are columns and rows. That's where these k's are sitting. And everywhere else in between, they are just zeros, right? So these are the only non-trivial entries. And so these are matrices acting on this vector psi, a and omega. And you see in particular that all the singularities here are regular, because all these z operators are regular operators, but there is an irregular singularity coming here. So there is an irregular singularity at infinity. So if you do a variable transform and you bring your z to you send your z to 1 over z and let it approach infinity, then you see that in fact this becomes irregular, because it will be 1 over your new variable squared. So this constant matrix A here produces an irregular singularity at infinity. So that's what I had promised you at the very beginning, that these conformal blocks have this kind of, they blow up at a certain point too steep and are irregular. And this is the theorem which proves that. And the second thing is, so this here defines for you a connection. If you view the right-hand side as the connection, and this connection is actually flat. So let me briefly present for you the proof of this theorem. So what you do is, for part 1, to show this differential equation, you do the following. So we proceed as follows. So you take del phi del zi, and then you differentiate. So your phi, we see that phi is defined in this way, as you can see here. Now you differentiate under the integral sign, okay? You differentiate under the integral sign, you will get minus ki over b squared times integral dw exponential of I 1 over w minus ci. So that's what you obtain. And this I was defined in this way here. And you take the second derivative, del zi squared. Then this is ki over b squared integral of the exponential of I prime, okay, d w minus z to the ki over b squared minus 1, where this I prime, or exponential of I prime, is the product j not equal to I, w minus cj to the kj over b squared e to the lambda over b squared w, and this is just minus ki over b squared. And then what you do is you partially integrate by letting this d operator hitting exponential of I prime. So you write it as exp I prime, and then w minus zi to the ki over b squared minus 1. And then, let me maybe write it a bit more here. You can write this thing as ki over b squared times minus lambda over b squared over ki del phi del zi plus. So this del phi del zi, this first piece here is obtained. You see this I prime has this piece which is exponential e to the lambda w, this exponential piece. So if this d operator here hits that exponential piece, it produces here this piece, and the rest is just can be restructured and recombined into just the first equation here. So that's how this appears. But if the exterior derivative hits the other terms, it just produces a bunch of other terms. So now we come to the other terms, where j is not equal to I, and we have kj over b squared, and you have dw exponential I 1 over w minus zi 1 over w minus zj. And this is when it just hits all the other terms. And then you can rewrite this as lambda over b squared del phi del zi minus ki kj over b to the fourth, j not equal to I, 1 over zi minus zj, integral dw e to the I, 1 over w minus zi minus 1 over w minus zj, and that's it. And then finally, you can rewrite everything, repackage everything as follows. Del phi del zi plus j not equal to I, 1 over zi minus zj, kj b squared del phi del zi minus ki b squared del phi del zj. And from this, you can finally say that, yeah, this is basically that equation which you had before. Okay, so that's how this acts, and right. So now, in order to prove the second part, namely the flat connection business, you just use that omega ij plus omega jk comma omega ik is 0 when I, j, k are distinct, and you also use that omega ij comma omega kl commute when I, j, kl are distinct. And once you do that, you can also show that this connection is actually flat, namely its curvature vanishes. And yeah, that kind of finishes off the proof.
Yeah, but there was this I matrix also involved in this.
Yeah, the I is also involved, but this is trivial because it's just so simple, this AI matrix. So it commutes just with all of the other guys.
Okay, but there is some condition between I's and...
Yeah, for the flatness, you have to take that into account as well. But that part is trivial, so I focused only on the omega ij's.
Okay.
Right? Good. So, yes. Now, what happens is that we still wanted to show our original equation, right? Now we have a vector valued first order equation. And the beautiful thing about this equation is in this equation, you see the C or DDC doesn't show up at all, right? So this is just a differential equation with respect to the Z parameters. And the C parameter doesn't show up at all. And but originally from the algebra point of view, we had derived this equation, the second order equation, which had also this DDC. But that one is just now a small lemma of this theorem. So you can use actually the result of the theorem, plug it in, let the other operator, the second order operator, actually act on this function f, which is something times the phi, and then use this theorem to actually show this following lemma. So if you have f gamma z in the 4-point function case defined to be some rescaled operator v minus k0 over 2b, v minus 1 over 2b z, v minus k1 over 2b1 I alpha lambda, right? Like this. So the modified PPZ equation becomes as follows: b squared del z squared minus 1 over z minus 1 over z minus 1 del z plus delta k1 c minus 1 squared plus delta k0 z squared plus 1 over z minus 1 c dc plus the alpha minus delta k1 minus delta k0 minus delta 1 minus c times alpha minus q over z minus c squared over 4 f gamma is equal to 0. So this just follows where now there is a crucial condition that alpha is b plus 1 plus k0 plus k1 divided by 2b. And this is actually, this differential equation is only satisfied if this condition for alpha holds. And that just is actually has a physical interpretation. So it comes out mathematically that that has to be the case, but physically, this is just the charge conservation condition I had talked about before. Because this alpha can be was a parameter of this irregular state, but it can be also interpreted as it's charged under this U1. And by Gauss' law, since we are on the sphere, the sum of all the charges has to vanish. And this is indeed the case. So it's a miracle that although our differential equation originally, the integral representation originally doesn't at all depend on any alpha, but the information about alpha is encoded in it and everything is consistent. So it all comes out nicely. And the original algebraic, the equation we had derived algebraically is also satisfied as a lemma of this theorem. So yeah, that's actually all I wanted to talk about today.
Okay. Thank you, Babak.